Assalamu alaikum. Hello everyone. Today I'm with you to present our work under title of optimization of scheduling algorithm for carrier aggregations toward quality of services requirements model in 5G LTE network, which is done by Ahmed Sabri, Haytham bin Abdel Mola, Amal al-Haj. Here I will give you the presentation outlines. First, I will start with the introductions and multi-carrier resource management framework, and then I will give you small introductions for the joint user scheduling scheme and its challenges. After that, I will present our proposed method under title with the improved fairness throughput delayed joint user scheduling construction, then simulation models, and after that the results and discussion. Finally, conclusion. Here I will give you small introductions about the LTE network, which is the wireless mobile network. Was standardized by 3GPP and introduced in 2011. LTE is advanced approach from LTE, which support various wireless broadband applications such as web TV, social network applications. Different services have a variety of quality of services obligations. The carrier aggregation is one of introduced technique for LTE systems to offer extreme bandwidth, where the main objective of carrier aggregation is to meet the improved mobile telecommunication advanced constraints with the peak downlink data rate of 1 gigabit per second and 100 megabit per second for low and high mobility respectively. Here or in this slide I will give you some introductions for the multi-carrier radio resource management framework. According to the new carrier aggregation technique for the LTE network, the new layer 3 component segment, as shown in this figure, has been introduced to allocate the users on a set of various component carriers. Moreover, one of the major radio resource management tasks is the bucket scheduler, which is responsible for allocating the component carriers physical resource blocks among users in an efficient manner. Also, at the beginning of each session, the base stations always executes of the adaptation or executes the link adaptations to establish a new radio carrier for the users according to the channel states, quality of service demands, and the current network load. Here, I explained the joint user scheduling scheme, which controls the numbers of component carriers by exploiting the capability of one resource scheduler. It's responsible for completely aggregating the processes for all carriers together as a single carrier. As demonstrated in this figure, the joint user scheduling places the physical resource blocks of all component carriers into the resource pool of a single resource scheduler. This means only single-level scheduling is needed, which enables the resource scheduler to map the service information to physical resource blocks of all carriers. We have two challenges for the joint user scheduling scheme, where the first one meet the quality of services requirements for real-time services such as packet delay, then the guarantee of minimum long-term throughput for non-real-time services. The focus on the development of joint user scheduling algorithm is to optimize the system-level quality of service in terms of system throughput and system fairness. From this table, we can see most of the previous study focus on how to optimize the user level and fairness index or the user throughput. But the last one, for our proposed method, which is under title Improved Fairness Throughput Delayed Joint User Schedule, I'm focused to optimize the user throughput and the fairness index By introduced the channel condition and the multi-services users. Uh, with low delay. Here I explain our process phases for this algorithm, which started with the bandwidth estimations, then the bandwidth allocations, and finally the resource scheduling. For the first phase, the bandwidth estimations, at each interval time transmission interval, the user reports high signal to noise ratio value back to the base stations. The scheduler then determines the eligibility of each resource blocks for the data transmission as follows equations. For all the active users, the demand data rate required by user K of the component carriers at time slot T can be achieved by allocating in resource blocks for the user K at time T with the specific modulation coding scheme as follows equations. The number of the required resource blocks at a time T for the user K is then calculated according to the following equations. Here I will explain the postcode for the bandwidth allocations, which started by calculating the bandwidth demanded for all active users, where the V is the offered bandwidth from the systems, sigma is the difference value between the offered and the demand data rates, Q is the total number of available component carriers, and I is the total number of user equipments. Here I will explain the resource scheduling algorithm flowchart, which started by start and then collect user instantaneous or collect the user's current throughput. Also collect the user's channel quality indicators feedback from the component carriers resource blocks. Also compute the user's head of line delay. After that, compute the priority scheduling based on the metric at the right side here. After calculate the priority metric for each users on each component carriers with the physical resource blocks, allocate the resources from the first and the second component carriers to users accordingly. Is there any left resources? If no, we will start from again to calculate the priority and allocate the physical resource blocks in each component carriers for the users. If the resources if there's no resources, allocate left resources fairly among users. Integer left resources the number of users. We will divide the rest of physical resource blocks equally among the users. Here I will explain the simulation modules. Some parameters, the system structures. We have 7 cells, 3 sectors per cell. The number of component carriers, 2 component carriers with 1.5 GHz. Side-to-side distance 500 meters. MIMO configurations 2 by 2. Also the component carriers bandwidth 20 MHz. Traffic model full buffer, traffic type is real-time and non-real-time, the number of users per sector 21 users, and the user equipment distribution is uniform. Here I will explain the results and discussions. For the fairness index, we can see in this slide the performance of the proposed scheduling algorithm is based on the fairness index. These figures show the algorithm performance by fairness index with respect to the number of users for VoIP users and video traffic flows. It can be noted by comparing the proposed algorithm with the other well-known scheduling algorithm in VoIP traffic at the left side that the better performance of 14.89 percent was obtained for the proposed algorithm over the exponential proportional fair joint user scheduling algorithm. Due to the improved fairness throughput delay, joint user scheduling is taking the head of line delay as scheduling metric. At the right side, for the video flow, the improved fairness throughput delay joint user scheduling algorithm shows around 20.22% improvement over the existing exponential proportional fair joint user scheduling algorithm. Now we will explain the achievement for the system throughput. As the number of users increases, the best channel quality indicators joint user scheduler shows about 10.94% better throughput performance for video and VoIP traffic compared to our proposed. On the other hand, the newly proposed algorithm achieves a higher system throughput than the exponential proportional fair joint user scheduling algorithm. This improvement is because the improved fairness throughput delay joint user scheduling algorithm minimizes packet loss due to deadline violation. And the achievement of best channel quality indicators joint user scheduler over our proposed method due to the best channel quality indicators allocates the physical resource blocks of each component carriers based on the channel status only. Here we explain the improvement of the packet delay for our proposed method. As you see at the left side for the packet delay for the VoIP flow, when the improved fairness throughput delay joint user scheduling scheme is used, the delay values for VoIP traffic is reduced as minimum as low with compared the other values of other scheduling algorithm. Also in the video traffic we can see the delay for our proposed method is the minimum value with the compared with the other scheduling algorithm. This is because the proposed improved fairness throughput delay joint user scheduling algorithm give the priority serving as many packets as possible before their deadline are reached. For VoIP and video traffic, a significant delay was observed when using the best channel quality indicator joint user scheduling algorithm. This is accurate because the algorithm gives the priority for the packet flows based on the throughput weight. Finally, in conclusion, in this study, the new resource management techniques for downlink transmission termed as improved fairness throughput delay joint user scheduling is proposed. To design this technique, the channel conditions and head of line delay have been considered. The proposed scheme has a good user level quality of service performance in terms of fairness, throughput, and the packet delay for active users. Thank you for your attention and questions.